Howdy. Welcome to the first virtual lecture for AGEC 317, Applied Production Economics. So the way this is going to work is I'm going to just walk you through the lecture material. So these slides are available on eCampus. If you're not enrolled in 317 and you're interested, these are also available in a link below. So I'm going to walk through this lecture material, and then at the end we will go through an example using Microsoft Excel. Okay? And then during the in-class portion of the class, we will talk through exactly the same example. And so I encourage you to watch this entire video all the way through, including the example. Try it yourself first, and then during the scheduled class time, we can discuss how to, or discuss any questions you may have. Okay, so production economics. So the good news is that prior to spring break and the COVID-19 interruption, class was very technical. So we talked a lot about building models, what made a good model, and how to decide between models. Right? It was very technical, very mathematical, and so the good news, I guess, is that for the remainder of the class, we will be focusing more on applications of those technical models. So at this point in the class, you should be able to build and interpret models, both simple and complicated, and know what makes a good model and what makes a bad model. And so now we're just going to apply those very technical skills again into some fun examples. Okay, so we're going to start with this module with production. So I'm going to go through a few examples just to get us started. This should be review, I guess, going back even to AGEC 105, your introductory ag economics course. So production is just the process of using inputs to create some good or service that has economic value to consumers. So if you're producing something, anything that somebody values, that process is production, simply put. A production function is the mathematical way that we represent that process. So there is a specific mathematical function that transforms inputs into output. Okay? And it's kind of just a classic function, right? So if we imagine a classic function y as a function of x, that function mathematically is treating x as some kind of input, and then a function is applied to that, and you get y as your output. So production function is exactly the same. So we're going to have inputs, but now instead of letters like x and z or w, now we're talking about actual goods that are inputs. So if you're talking about agriculture, seeds and fertilizer, classic inputs, and your output is going to be whatever you're growing. So the production function is the actual mathematical formula for that production process. The short run is any time horizon where there are some fixed costs, and the long run time horizon is any period where all the costs are variable. So you should be aware of what fixed and variable costs are. Variable costs are costs that change with your level of output. Fixed costs are costs that are constant regardless of your level of output. Okay. For this module, we're a little bit short on time, so we're going to be focusing primarily on the short run. Okay, the production function here is in a general form. Q is our quantity produced as a function of x, y, which are just different inputs. Okay, we call the MPP, or the marginal physical product of some input x, is the partial derivative of your production function with respect to x. So remember, Q here is your production function. If you take the derivative of Q with respect to x, you get your marginal physical product of x. So this production function is a function of two inputs, x and y. That means we will be able to calculate a marginal physical product of x and a marginal physical product of y. And all that is doing is measuring the change in output for a unit increase in whatever input we're talking about. Okay. Average physical product is a lot easier to calculate. It is just the ratio of total output to the amount of some input. So the average physical product of X is going to be our production at some level And at that level of production, we just divide that by the amount of input that we're using to reach that level of production, and we're going to get this APP, average physical product. So these definitions should sound a little familiar. So this is a figure from your AgEc 105 book, if you took AgEc 105 at Texas A&M. This is showing the relationship between marginal physical product and average physical product. So the x-axis here is labor use. So the input we're talking about here is labor, and output is abstracted here. We're just producing something. And the y-axis is our measurement of MPP and APP. Okay, so the different so marginal physical product and average physical product change as we change our amount of inputs. So we'll focus on MPP, marginal physical product. In an ideal setting, usually we experience some kind of rise in MPP. It peaks and then it comes down, eventually hitting 0 and then on to a negative number. So what this means is, let's say we're at 16 here. So we're using 16 hours of labor to produce our good. Now, if we were to increase our labor use by 1 unit, so move from 16 to 17, so that's hiring or just using one more additional hour of labor input, then the marginal physical product is going to be, let's say, about 0.35, meaning that we'll get 0.35 more units of output if we use an extra hour of labor. And as we use more labor, that's going to change. So let's now say we're at 22. If we go from 22 hours of labor to 23 hours of labor, now the MPP is up here at over 0.8, meaning that as we go from 22 to 23 hours of labor usage, we should expect a 0.9 unit increase in our produced good. Okay. So MPP is not constant. It's changing as we're using different levels of input, and same with APP, the average physical product. So APP has usually a more flattened curve, but not always. It can look different for different types of industries. And so again, this measurement is just our total production divided by the input we're using. So here, let's focus on this dot here. So at this point, we are using 20 hours of labor, and we're producing some amount of good. So that amount of good that we're producing divided by 20 looks to be about 0.2. Okay, that means just on average, a unit of labor use, which is an hour of labor, is producing 0.2 units of a good. Okay, so that's all these curves really mean. But the relationship between MPP and APP turns out to be very important. So it defines the 3 stages of production. So stage 1 of production is when our MPP is greater than APP. Okay, so marginal physical product being greater than the average physical product is this area here. As long as MPP is greater, we say we are in stage 1 of production. Then they cross, they intersect, and then after that, APP is greater than MPP. We call that stage 2, and stage 2 continues until our MPP gets to 0. When MPP gets to 0, then we're going to enter stage 3 of production. Okay, these are all just names for different aspects of the production process, but if you'll remember from earlier classes, we would like to be in stage 2 of production. So here are the mathematical explanations for the different stages you can see on the graph on the previous slide. So if we're operating in stage 1, it's not desirable. We can do better, because if we increase the use of our input, then on average, we're still going to be increasing our output. So our APP is going to be increasing as long as we're increasing our input. So in stage 1, we want to continue to use more and more input to produce our good. Right? And so we're going to keep going. So if we go back to our graph here, we're in stage 1. We're going to, if we're operating here, if we increase our labor usage, on average, our production is going up. which means we want to do that. So we're going to keep going and going and going. And so there's this force, invisible force, that's pushing us. When we're in stage 1, we should want to increase our labor. And we're going to increase it and increase it and increase it until we reach stage 2. I want to skip stage 2 for a second. If we increase it to the point where we're in stage 3, that's bad because our marginal physical product is now negative. What that means is if we hire an additional person or we use one more hour of labor in this stage 3, our output is actually going to decrease. So, I mean, that's a very clearly a bad thing. So that means, just imagine if you're a big fast food chain, you hire an additional worker, you're currently making, let's say, 40 hamburgers an hour. If you hire an additional worker, that drops to, say, 35 hamburgers an hour. That's an objectively bad thing because you're losing on output. You've lost 4 or 5 hamburgers, and you're having to pay this additional person. So it's very clearly a loss. So stage 3 is not desirable, which leaves stage 2. So stage 2 is the stage of production that we would like to be in, and there is this kind of force here to continue to produce in stage 2 up almost until we get into stage 3. But again, we don't want to be in stage 3. So stage 2 is good. Really, there's a lot of area here in stage 2 that we can operate in that is okay, and that's good. We really want to just avoid operating in stage 1 and avoid operating in stage 3. Those are the red zones. Okay, so that's just a review. Finally, we have the elasticity of production. So this elasticity is measured in a way most elasticities are measured. So the percent change in our quantity produced given a percent change in our input use can be rewritten as this function here. So this is the partial derivative of our output with respect to our input x multiplied by the input x divided by the, this y should be q, okay, output. So that's the elasticity of production that says for a 1% increase in our input x, by what percent is our production going to change? That's this elasticity measure. And this first portion here should look familiar. That's just MPP. And this second component here should look familiar. That's the inverse of APP, or 1 over APP. So if you have MPP and APP, then we can estimate the elasticity of production by just dividing MPP by APP. Okay, a cool feature. Okay, law of diminishing returns. This is just something to be aware of. Eventually, you're going to get less bang for the buck, so you should be very aware of this economic law. What this states is just eventually you're going to be using so much input to produce something that getting additional input is going to decrease the marginal return that you get from that input. So pretty straightforward stuff. Okay, so let's suppose that we have a production function, this Q, as a function of 2 inputs, x and y. How can we find the optimal level of production? So this is also the same way as saying, how do we maximize our output? So if we have our production function here, and it's just a function that we can maximize, then all we need to do here is take the partial derivative of our production function with respect to our inputs. So that's going to be the partial of this function f with respect to x, which is by definition the MPP of x, and we set that equal to 0. Okay, and then we also have to do that for y because we're using 2 inputs, both x and y. And so if we don't have any constraints and we want to maximize production, then what we need to do is find our marginal physical product for each input, set that equal to 0, and now we have a system of equations. We have 2 equations here that we need to solve for and 2 unknowns, which is the optimal level of x and the optimal level of y. So we can solve there for the optimal level of both inputs. That's going to maximize our production. Yeah, that's a very simple case with no constraints whatsoever. So that's good, that's fine, but how do we know what the production function looks like? So everything depends on that. the determination of which or how much input to use is a function of this optimization problem where we are taking the derivative, partial derivative, of this production function. So without knowing what this function looks like, we cannot find the optimal level. So if we do want to find the optimal level, we have to know what this function looks like. And that function is often given to us in our early textbooks, but in the real world, we don't just get that function. We have to estimate that function using data. Okay, so that's our job as economists, is to estimate that production function. So again, here is the curve, the curves we talked about earlier, MPP and APP. And at this point, you should say, okay, these curves look kind of like upside down U's. So if we have data on production, what kind of model should we specify? If we want to see an upside down U curve, then there's one clear winner. And that's going to be a quadratic model. So a quadratic model allows us to estimate an upside down U-shaped curve. Perfect. That's exactly what we want, because economic theory tells us that MPP and APP should both generally have an upside down U-shape. So a quadratic model is something that we can specify given some real world data, and that's going to allow us to calculate APP and also solve for the optimal level of input. Okay, we can also use a Cobb-Douglas function. That's a log-log model, and we'll talk about that in just a second. So let's say we have a quadratic model. Let's say we were producing something, some amount Q, and that production is a function of capital inputs and labor inputs. So if we have information, we have data on outputs, and we have information on given some I level of output, what is the amount of capital and labor that was used to produce that? Then we can create new variables, which are the square of the capital and square of labor. And we can estimate this function, and we can get estimates for beta naught, beta 1, beta 2, beta 3, beta 4. Right? This is just the classic quadratic model that we've been working with. So once we have that, then we can solve for the optimal level of capital and labor. Right? So even before we run the regression, we can take the partial derivative of our production with respect to capital, which is just going to be beta 1 plus 2 beta 2 times capital. Set that equal to 0. And then we see that the optimal level of capital is going to be negative beta 1 divided by 2 times beta 2. Okay. So at that point, we know the optimal level of capital, and similarly, same process, the optimal level of labor is just this expression here. What is beta 1 and what is beta 2? Well, that comes directly from our estimation, our econometric model. So once we run this top regression here, we can just plug in our estimate for beta 1, plug in our estimate for beta 2, and perform this calculation, and that's going to give us the optimal level of capital. That's the level of capital that's going to maximize our production, Q, okay? And similarly with labor, okay? Now let's say that we have a log-log model. This is a Cobb-Douglas production function. So now quantity is still a function of K, which is capital, and L, which is labor, but now it just has a different functional form. So we cannot run this regression as it is right here. What we need to do is take the log of both sides, and that's, as we talked about in class, is just going to give us this functional form here. The log of quantity produced is now a function of the log of A plus alpha times log of K plus beta times log of L. Okay? So that's our new functional form. Now we can run that regression. Once we run this regression, we're going to get estimates for alpha and beta. And then we can essentially just exponentiate both sides here and get back to our original Cobb-Douglas production function. But now we know what alpha is, and now we know what beta is, and then we also will have an estimate of what A is. Okay. So now this is again just an analytical solution. The partial derivative of our production function with respect to capital is this expression here. Now if we solve for K, in this case, the optimal level of capital, we're going to get that the optimal level of capital is going to be equal to beta divided by A times our level of labor. Okay, so in this case, in the same similar situation for optimal level of labor. You should be able to do this algebra here. So what does that mean? Well, if we want to know what the optimal level of capital to use, then we're going to have to fix labor at some level. And given that fixed level of labor, we have estimates for beta and estimates for alpha, so we can just perform this expression, and we get the optimal level of capital to use to produce our good. Okay. So this is using optimization and econometrics hand in hand. Okay. So these are both more simple examples. It gets a lot more complicated if we have constraints. So if we had a constrained optimization problem, we wouldn't just have, I'm going to go back a couple slides, these two first order conditions, right? So this is the first order condition with respect to capital, first order condition with respect to labor. If we had a constraint, then we would have a new first order condition with respect to lambda, which is the Lagrange multiplier. Okay. So for every constraint that we have, we're going to have an additional first order constraint, which means an additional unknown and an additional equation. So we can still solve for optimal levels of input. It just becomes a little bit more complicated. Okay. So the process itself is relatively simple. What we do is we observe data, and then we use OLS to predict an appropriate model, to find a good model to fit the production data. Then we use that model to form an optimization problem, and then we solve the optimization problem. So that means we can go from data all the way through to answering a very specific question, which is, finding the optimal level of an input to use. It's a very important question. But we're going to make it a little bit more complicated. So our goal is seldom to simply maximize output. A lot of times we want to minimize costs or maximize profit. Those are the things that typically we're more concerned with than just the output. So a few more definitions. We have total value product. Total value product of inputs is just the production function multiplied by P, which is the price of the sold output. So that's just going to give us the total value product. This is also very similar to total revenue. So we're going to get what we're producing multiplied by the market price of what we're producing, and that's going to give us the money that we're bringing in, or the value of the product that we're selling on the market and producing. Okay. The marginal value product is just our MVP. Oh, sorry. MVP is the marginal value product. That's going to be equal to price times the marginal physical product. So the MPP that we calculated before, which is just the partial derivative of production with respect to an input X, multiply that by P, which again is the price of the sold output, and that's going to give you the marginal value product. Similar way to calculate average value product. And then finally, we have the total cost function represented here by C. This function is going to be a function of the price of the inputs multiplied by the amount of input we use. So if we're using some amount of X input, we want to multiply that by the price of that input and add that to the other price of the other input times the other input that we're using, and then add this B, which is going to be some fixed cost. So this is going to be the total cost that we incur by purchasing X and Y inputs to produce our good. Okay, and then profit is just putting all those things together. So we're going to have this market price times Q, which is what we're producing. So this first portion here is going to be our total revenue, and then minus total costs. So minus the cost of using X input, minus the cost of using Y input, and then minus the fixed cost. We represent this entire profit function by this pi. Okay, so what is Q? Q is our production function. And so if we specify a quadratic form of the production function, it's going to look like this, right? So this is the capital and labor quadratic function that we specified earlier. So now our profit function is this big thing here, and we can find these betas by performing OLS regression, and then we just observe the prices here and the fixed costs. Okay? Cool. So now let's look at the production process for toilet paper. It seems to be on people's minds. So if we're producing toilet paper, there's a lot of inputs that go into producing anything. But to produce toilet paper, let's say that we use human labor, electricity to run the machines, some recycled paper, glue to hold the cardboard and the rolls together, and then some bleach to color the paper. Okay. So we can produce a pretty complicated production function if we're considering truly all of the inputs for the production process. For now, we're just going to look at the electricity that's used to run the machines and then recycled paper. Okay. So let's say we're going to use a quadratic model again. So our profit now is P times Q. Q is this big function here, which is a quadratic function of electricity and paper inputs. And we subtract off total cost, which is the unit cost of paper minus the unit cost of electricity. Sorry, each of those multiplied by the amount of paper and electricity that we're using, and then minus total cost B. So what is the optimal amount of electricity and recycled paper to use if we want to maximize profit? Again, not considering any constraints. Well, we just want to take the partial derivative of profit with respect to electricity. Again, you should be able to do this derivative. That's going to give us this function here. Price times beta 1 plus 2 beta 2 minus the unit price of electricity. And actually, there's something missing here. There should be an electricity term here. Okay. And so if we solve for optimal electricity, again, that term, apologize for the typo, should be right here. Then we just are doing algebra, and we'll find that the optimal level of electricity is this term here, which is unit price of electricity divided by the price of toilet paper minus beta 1 divided by 2 times beta 2. And these two come from the regression. So if we have our data, we run one regression. It's a very simple calculation then to solve for the optimal amount of electricity that's going to maximize our profits. Okay, which is a very, very cool thing if you're a producer of toilet paper. And we can do exactly the same thing with recycled paper. Okay, so what if we have a budget constraint? So again, that's going to be adding in a Lagrangian, right? So if we only have a certain budget to purchase electricity and toilet paper, that's going to affect the amount of electricity and paper that we can purchase. And so the solution is going to be a bit more complicated, but again, it's just from an optimization problem, we're just adding a Lagrangian, making it a constrained optimization. Okay, so now let's solve a real-world production problem. So this is where it gets fun. Our data here, which is again data on lentil production. So you see we have yield in bushels per hectare, nitrogen usage in gallons per hectare. Nitrogen squared is just the squared term, the squared version of nitrogen. Seed pop is the number of seed packets that were used per hectare. And then we have a interaction term, which is the just interaction between the number of seed packets and amount of nitrogen. And then finally, this dummy variable on ownership. Okay, so there's two models we could, there are a lot of models, right? So there are 1, 2, 3, 4, 5, 6 right-hand side variables, and we could use any one of them or any combination of them to try and formulate a model. So there's a lot of options here. But if we want a quadratic model, one simple version is to just use yield as a function of nitrogen and seed inputs and make that a quadratic function. Okay, then we're going to get 5 parameters here. And then another option is to specify yield as a function of the inputs, nitrogen and seed inputs, make that quadratic, but then also add this interaction term and the ownership dummy variable. So I'll leave it to you to estimate this first one and compare it to what we'll see here as going to be ultimately the best model. Okay, so go ahead and try and run this regression by yourself, and you can run through everything we're about to do using this specification. But for now, I'm going to assume this a little bit more complicated specification. As it turns out, that's going to be a better model fit. Okay, so let's run this second specification, which is essentially yield. It's a function of all 6 of these variables. Okay, everything's set up nice and ready to go. We don't need to move anything around. We don't need to create any new variables. That's been done for us. So all we need to do here is run the regression. So the regression results are actually already on this second tab, but just to be thorough, we'll run the regression ourselves real quick. So if you go to data, data analysis, hit regression, our Y range is going to be the yield column, including the label. The X range is going to be all 6 of these variables: nitrogen, nitrogen squared, seed, seed squared, the interaction, and dummy variable. So all those observations. Include the labels, and let's send this new regression output to a new sheet. We'll just call it test. Okay. Okay. And there we get our regression results. So actually I'm going to flip over to the main tab. They're going to have identical results, but this is already zoomed in, which is nice. Okay, so as we can see, we're looking at the adjusted R squared. Really great. So 0.989, meaning the 6 explanatory variables we have are explaining 98.99% of the variation in yield, which is pretty incredible. The f-test here, the p-value on the f-test is highly significant, meaning that our model is jointly significant, meaning that at least one of these 5 coefficients here are significant. Good. And then finally we can look at the p-value, and again, if we're assuming alpha of 0.05, we can see that, as it turns out, all of these coefficients are significant. So we can take all of these coefficients as given. So now what we've done, if we go back to the data tab, is this function here, which is our production function. Now we've specified it, meaning that, or we've estimated it, meaning that we have numbers for beta 1, beta 2, beta 3, all the way through beta 7. Okay. So if we go over to the optimize tab, then what we can do, I've just copied and pasted the results, the coefficient results here for each of the coefficients. So I'm going to encourage you to do the same. You're just copying that table and pasting here. And now we can set up a solver problem. So we have 4 different tables. I'll explain each one individually here. So here is nitrogen use and seed population or seed packets, and then ownership. So these values here, if we look at each of the individual cells, let me zoom in a little bit more. These have no formulas, right? So these are values that we can change. So just for an example, let's say I'm going to, instead of using 45 gallons of nitrogen, I'm going to use 23. That's going to change everything in our sheet. And seed population, I want to use 5 packets. Okay. Ownership, we can set that equal to 1 or 0. So if it's 0, this means it's a independently operated farm. If it's 1, then that farm is monitored by our organization, our Lentils and More. So let's say ownership is equal to 1. Okay, costs. So we have variable costs and fixed costs. Right now, I've just considered fixed costs to be 0. And the variable costs here, these are functions. So let's focus on nitrogen. So what is the variable cost of nitrogen? If we hit function F2 or just F2, we can see the formula for this cell. So this is going to be equal to the amount of nitrogen we're using multiplied by the per unit cost of nitrogen. Okay. So if nitrogen costs $3.5 per gallon and we're using 23 gallons, well, then we're going to incur a cost of $80.50. Okay. Similar case for seed. So we're using 5 packets and each packet costs $2.56. which means that we're spending $12.80 on seeds. Okay, again, all this is per hectare. So total costs is just going to be the sum of all the variable costs and the fixed costs. That's it. For our revenue, this lentil production, this is the amount of lentils that we're producing in bushels. Okay, I'm going to skip over that for just a second. That's the most complicated formula. Our total revenue is going to be that production amount multiplied by the market price. So right now, if lentils are selling for $8.50 a bushel, and we're producing almost 200 bushels, then that means in terms of revenue, we're making almost $1,700 in revenue. But again, we're incurring almost $100 in costs, meaning that our profit is up roughly around $1,600. Okay? So the one cell I skipped over is this lentil production. So if we look at the formula for that, it's very complicated, but all it is the econometric model that we specified in the first sheet, right? So our production in lentils is going to be equal to this intercept term plus the coefficient on nitrogen times the amount of nitrogen we're using plus the coefficient on nitrogen squared multiplied by the amount of nitrogen we're using squared plus the coefficient on seed multiplied by the number of seeds we're producing, etc., etc. You should be able to follow this through and recreate this yourself. And then the last one we have is the coefficient on ownership multiplied by the value for ownership, which in this case is just 1. Okay. So given our model results, we can predict or calculate exactly what our predicted production is going to be given our inputs, right? So we can change these input amounts, and that's going to change our production. So if instead of 23, we're using 230 gallons of nitrogen, that's going to change how much we're producing. Actually, as it turns out, not by much. Let's do something really insane like 500. This is kind of a nonsensical amount, but at this rate, if we're applying 500 gallons of nitrogen, we're actually losing. So here our production is negative, which means we're burning the field, right? So it's not good to use too much. If we're using barely any at all, we get a different amount of production. Okay. So that's all good. That's great. And our goal here is profit, right? We want to maximize this number here. So we can do, okay, so we're going to buy 5 seed packets. We're going to have ownership have oversight by the company. And now let's just see if we can change our nitrogen usage to try and maximize our profit. So let's go from 1 gallon to 2 gallons. Okay, profit went up by a little bit. Let's try 3 gallons. It went up by a little bit. 4 gallons, up by a little bit. 5 gallons, up by a little bit. We can do that for a very long time to guess the exact amount of nitrogen that we need that's going to maximize our profit. And that's just keeping seed and ownership fixed. If we're also changing seed and we're changing both of these numbers at once, we could play the guessing game for a very long time to try and maximize profit. So to actually get the true number, the actual maximal amount of profit and the values of these inputs that's going to maximize that profit, there's 2 ways. One, we can use math, like the derivative that we did in the actual lecture, and solve for it and just use these parameters whenever we need to and calculate by hand the optimal level of nitrogen in seeds. Or we can use Solver. And Solver is a pretty neat Excel tool that is good to know about. So we'll go ahead and use that. It turns out to be a lot easier too. So if we go over to our data tab, past data analysis, and go to this additional add-in Solver, we click on that. And so we're going to do a few things. First, it's going to ask us to set our objective. This objective is what we want to minimize or maximize. So we're going to set our objective here to just the profit cell, right? We want to try and maximize profit. So that's our objective. What do we want to do? We want to max, min, or set it to some value. Well, we definitely want to maximize profit. Okay. How are we going to do that? We're going to tell Excel, you can change certain cells to find the maximum profit. Which cells? Well, our two inputs. I'm going to highlight both of those input cells, and that's going to give Excel the authority to change what here is B2 and B3, change the level of nitrogen and seed inputs to try and find the maximum solution of profit. Okay. And we can add constraints if we want to. Right now, we're not going to do any constraints. So this is just unconstrained optimization problem. And that's it. So we have our objective function. We want to maximize that profit by changing the level of inputs. If we hit solve, it takes Excel sometimes a few seconds, depending on the speed of your machine. And it's going to pop up with the solver results. So here we go. It says we have converged the current solution. We're going to keep the solver solution. Okay, hit OK. And we just want to know what these inputs are. So apparently, if we use 45.5 gallons of nitrogen and 12 seed packets per hectare, that is the optimal amount of those inputs to use if we want to maximize profit. So this profit here of $1,800 or $1,811 is the maximum amount of profit that we can achieve. There's no way we can have different amounts of these inputs and get a higher profit. So we've maximized profit, and we know exactly how much nitrogen and seeds that we should buy per hectare for the lentil operations. Right? So this is pretty cool stuff. So again, all we were given was this data, right? Data for an individual field on production, how much nitrogen they were using, how many seed packets they were using, and whether it was owned independently or had some oversight from a multinational corporation, right? For a lot of fields, as it turns out, for 96 fields. That's it. And with that, just that information, we're now able to say that on average, a farm should purchase 45 gallons of nitrogen and 12 packets of seeds if they want to maximize their profit. Okay. Again, pretty cool stuff and pretty straightforward. And the key to all of it, to be able to do any of this stuff, is this functional form. So if we go back to our econometric model, if we didn't have this, and we weren't able to estimate this model, then we wouldn't be able to do any of the optimization process, right? Cool. So that we've achieved our main goal. We have our optimal level of inputs. And then the secondary goal, if you'll remember, is to look at the production stages. So again, I just copied and pasted the coefficient estimates here. I'm going to fix ownership to be equal to 1, and I'm going to fix the number of seed packets to be equal to 20. And now for the different levels of nitrogen, we can solve for TPP, MPP, and APP. Okay. So this graph here is just showing the relationship between marginal physical product and average physical product. And as we can see, APP is higher than MPP across this range of nitrogen, meaning that if we're in this range of production or input use for nitrogen, then we will be operating in stage 2 of production, which is what we want to do. So this range is good. We can continue these curves outward. Eventually APP is going to, eventually MPP is going to go to a negative number, and that's going to be the beginning of stage 3. We want to avoid that. And if we go back, in this case, actually, it's not the case, but for some industries, we may see stage 1 of production, which is where MPP is greater than APP. Okay. So how do we calculate these things? I encourage you to look at these formulas. But again, this total physical product is just going to be, again, how much we're producing. So this formula here is pretty complicated, but it's no different from what we did in the previous sheet, where we're using the coefficient estimates and the econometric model to predict how much how much lentils we're producing, given this ownership, this number of seed packets, and this level of nitrogen. Okay. And then the MPP is just going to be if we take the derivative of TPP and we fill in all of the coefficients and levels of seed packets and nitrogen, we'll get the marginal physical product, and then average physical product is pretty simply total physical product divided by the input usage. Okay. And then from there, all we do is just we can graph it so we can visually see that APP is greater than MPP. Okay. So that's it. That's the example. So we've taken raw data, we've specified an econometric model here, and we use the results of that model to solve for the optimal level of nitrogen in seeds to purchase to maximize our profit. And we also ensured that we are operating in stage 2 of production. Okay.